Okay, thank you, Shai, for the introduction. I will talk today about reducing microbial load alongst the alongst the fish poultry processing chain. As Shai mentioned, I am a research scientist based at Marel Poultry, where I'm responsible for microbiology and hygiene. And we are based in Boxmeer in the Netherlands. In my talk today, I will like to give a brief overview of the methods you can use to reduce microbial loads along the fresh poultry processing chain. Thereafter, I'll give, let's say, an idea of or an example of the experimental work we've done to try to reduce microbial load, in this case study on fresh breast fillets. And thereafter, I'll give some perspectives. Now, when the bird arrives at the slaughterhouse, it is carrying a large microbial load. And this microbial load is distributed on both the external as well as the internal surfaces. Externally, it is on all surfaces, so including the feathers, the skin, but also on the head and the feet. And then internally, it is distributed along the gastrointestinal tract, so including here, I've given an example of the crop and the cecum, which carry quite a large microbial load. Normally, in a healthy bird, muscle that is covered by the skin is considered to be sterile. But during processing, we transform these live birds into various products that you can see over there, including whole chickens, but also various cuts or portions, which may be with or without bone or with or without skin. But what is important in that transformation is that the contamination itself is then limited to only 3 prime locations, or what we call new surfaces. Those are, for instance, the internal cavity, which is created during the evisceration process. We also have exposed muscle tissue, which is created mostly in the cut-up phase of the process, but also the skin itself. There a number of new surfaces emerge during the process, especially at the defeathering stage, whereby the follicles are opened up, and also you create what are called deep dermal channels that are contaminated immediately by the picking water, but also the skin itself, the top layer, that becomes a new surface, because there you have the removal of the epidermis, either partially or fully, creating a complete new surface. Now, efforts to actually reduce, let's say, contamination itself start actually before the birds arrive. Remember, I said that they arrive with a large microbial load on them. So the efforts to reduce normally start before this. And these include efforts, for example, in the rearing or breeding phase, whereby the focus is mostly on reducing the prevalence of important pathogens such as Salmonella and Campylobacter. And then afterwards, you move to your, so your pre-slaughter phase, where you have important activities that can reduce the microbial load, such as your feed withdrawal management or strategy, as well as transport and lairage. These are very important in reducing the microbial load that enters the process, what we call the infeed, either internally, so the gastrointestinal tract, or on the external surfaces of the products themselves. Once they have arrived at the plant and then you start your processing, there's 2 main things that you can do to reduce the microbial load. The first is that we urge that you perform or you take some measures that can reduce the risk of contamination itself. So you address all the microbial risks that you encounter along the processing line. And secondly, obviously, contamination is going to occur at some stage. There you can take some measures to reduce the level of contamination on the product itself. In my talk, as I mentioned today, I will try to focus mostly on that aspect of the process itself, and not the first one. It's not that it's not important, but because of the time, I will just focus on that aspect over there. Now, actually reducing the risk, so the potential of contamination itself, paramount is your process hygiene. This is really, really important. And obviously, in most countries where we have commercial poultry processing industries, there you have also mandatory process hygiene criteria that are enforced by local food safety authorities. These really help or form the bedrock, especially in Europe, for the production of safe, let's say, products, because they were not allowed to use chemicals to decontaminate the products. So we have to operate or process as hygienically as possible. Secondly is you need really a robust risk-based food safety and quality management system in place, because and in most countries, again, the minimum requirement is to have either HACCP or its equivalent, and this allows you to then identify, to monitor and to control those hazards before they get out of hand. And then thirdly is you also can look at your process management itself. This is very important. I've only listed a few examples there, but it extends to even the culture within the organization, how you approach your microbiology, your hygiene, and your food safety. How you approach those can be enlisted in this process management. As an example, I give here logistic processing. If you apply this, this simply implies segregating your salmonella positive flocks during layerage and then only processing them at the end of the day, which allows you to reduce the salmonella load on your processing lines, but thereby reducing also the risk of contamination. Also, the layout of the plant is an example of how you can reduce your microbial risk or risk of contamination. In this case, important is your product flow, your airflow, and your personnel flows. I've included here a small picture that shows you, for instance, for airflow and product flow, these are in opposite directions. Your air is normally flowing from the clean part of the process, whilst your product is flowing in the opposite direction, which allows you to reduce the risk of air being a source or a vector of contamination. And then your personnel flow is normally on the periphery of those processes, and obviously you would want to separate personnel who are working in the clean and the dirty parts of the process. Also, I'd forgotten to mention, you also should look at continuous improvement, and this is not only continuous improvement of your process or your process hygiene, but also the performance of your food safety and quality management system and other aspects of your process management. We see actions on 4 levels, or practical actions that can be taken at 4 levels. So those include actions that can be taken at the level of the product, the equipment, the process, as well as the environment. With regards to, I can mention as an example for the equipment, I'm from an equipment manufacturer, the role or the main aim is try to limit damage of the product. That may increase the microbial load on the processing line or result in contamination of the product. We are also looking at limiting the role of the machine as a source or vector of contamination, and also important as well, what we take really seriously is hygienic design, as this helps to reduce the microbial risks or risk of contamination in the line. For the process aspects, this is simply maximizing those aspects of the process that are beneficial microbiologically. So, for example, aspects that may remove or inactivate the microorganisms. With regards to actual reduction, let's say, of the bacteria themselves, or when contamination occurs, there are a number of ways that can be done, but there are 2 main groups. You can either remove the microorganisms or you can inactivate them. And in removal, there are a few examples given there. So, for example, washing. You can trim, for example, removal of the neck fat or the neck skin or the crop fat, which are highly contaminated. You can also use brushing, either in combination with water, to reduce the microbial load on the product. And activation can be physical or chemical. Under physical, mostly steam, I think, and ultrasound. These have found a small foot, have managed to gain a small foot like a small footprint in the commercial sector. It's not yet widespread available, but there are some companies that are now using this. The other techniques that I mentioned, these are mostly in literature, but commercial applications are not yet widespread. For commercial, so the chemical inactivation, there in the European Union, we are not allowed to use chemical decontaminants, as I mentioned before. You're only allowed to use potable water as a processing aid. But obviously here in the United States, where we have mostly water chilling systems, there you can use, for example, the main 3 organic acids, your inorganic phosphates, and your inorganic or organic chlorine-based agents. Also important is that a lot of other compounds have also been investigated that you find in literature, but again, commercial applications are still not yet, let's say, widespread. This may be related to effect on product quality, it may be related to cost, or it may be related to difficulties in integrating that technique within the current processing lines. Now, I will move on to what I mentioned before. That's just an example of the experimental work we've been doing ourselves, in this case, to reduce the microbial load that occurs on breast fillets. So now these fillets, these are very important products economically for poultry processors. And what we notice is that the fillets themselves, the filleting process has a significant effect on the microbiological status of the breast tissue. Within a very few, within 10, 15 seconds of automated filleting, you go from having more or less sterile breast tissue to contaminated tissue, which can have an impact on not only on the shelf life, but also can compromise the food safety of those breast fillets. I've included here a graph that shows you some previous work we had done, which shows you the impact of actually the automated filleting on the microbial contamination or the microbial status of the top side of the fillet. And in this case, these are the TVCs, or total viable counts, is measured in terms of log of colony-forming units per centimeter squared of the top side of the fillets. There you notice that when you move from before filleting to after the filleting, you have an almost 2 log increase in the contamination levels. And then afterwards, these remain more or less stable. So after manual trimming and packaging, there's just more or less cross-contamination that is actually happening. So with this, we were then asked the question, where does contamination occur within that automated filleting machine? To address this question, what we actually did is we set up an experiment to determine the microbial dynamics within the filleting machine. So what we did is we looked at the contamination levels on the fillets before and after each module of the automated filleting machine. Those are the ones that are in blue, so the de-skinner, the wishbone remover, the halver, and the separator. And what we did is we looked at not only the top side, but we also looked at the cut tissue, so what is the bottom side of that fillet, and also what we call the crop area of the fillet. So that is the area where the crop was previously attached to the breast on the carcass itself. We also looked at differences in contamination between a clean and a used automated filleting line. As an example of the results you obtained, so for the top side, I have a graph here that shows you the numbers of bacteria that were actually added per module or in each module on a clean and a used line, and in this case, still on the top side of the fillet, and in this case, again, the total viable counts, where you can see that the de-skinner and the wishbone remover are the ones that really were adding bacteria to the top side of the fillet. Afterwards, there was more exchange, so cross-contamination in the remaining 2 modules of the automated filleter. And you can also see clearly that on a used line, so after, let's say, about 2 hours of use, when the line is more contaminated, there you have a higher contamination or more bacteria being added to the top sides of the fillets. This already gave us the idea that if you would more frequently clean these 2 modules, so the de-skinner and the wishbone remover, you could already address part of the problem regarding the contamination of the top side of the fillets. Thereafter, we also looked, as I mentioned before, at the cut tissue, so the bottom side of the fillet. And there we determined that all the modules which are actually cutting the fillets, that these are contributing or introducing bacteria to the fillets. So for example, the wishbone remover, the halver, and the separator. But as you can see as well, once the lines became a bit contaminated, especially for the wishbone remover, they were adding a lot more bacteria to the bottom or the cut side of those breast fillets. And then again, that suggests again that if we would more frequently clean these units, we could reduce the contamination level on the bottom side of the fillet as well. An important thing we also noticed, which kind of like changed our trajectory of this investigation, was that that crop area of the fillet, we determined that it was actually the most contaminated part of the breast fillet before the automated filleter and also after the automated filleter, and therefore was microbially limiting in terms of shelf life or even food safety. And there I show that you can see on the picture on the right that the tissue in the crop area has about approximately 4.3 log CFU per centimeter squared in terms of the total viable counts, whilst the cut and the top side are ranging between 2 and 3.2 log. So there's almost like a 1 to 2 log difference compared to the crop tissue. So that is really the microbial limiting part of the breast fillets. Once we did this, then the question was, okay, where is this tissue actually contaminated in the process? Because if we address all the other things, so we make it that the wishbone removal, the disc skin are working more efficiently or causing causeless contamination, we still have the problem that the crop area is microbially limiting. So where can we actually reduce contamination in that area, or where has it been contaminated, to help improve the overall quality of the fillets? There we set up one more test, and in that test we were looking at actually trying to look at where we would find the initial point of contamination of that crop area. We had a clue, and the clue was that there were high lactic acid bacteria on that crop area tissue. So we decided to look at crop damage as a source of contamination. For that part, we simply went to the eviscerator and we looked at the breast tissue still in that crop area from carcasses that had intact and damaged crops. And what we found, you can see in the graph that I have on the right, that indeed crop damage was at the eviscerator was what was causing contamination of that, the tissue in that crop area. And you can see that there's almost a 1.5 log increase for the Enterobacteriaceae, which are the ENTs. There's a 1.8 log increase for the total viable counts, and almost a 2.4 log increase for the lactic acid bacteria. Again, that's a marker of crop damage. When we had this, then there came a question that, okay, we are a provider of solutions in the poultry industry. If we provide or make a solution that can, let's say, prevent crop damage, would the benefits of preventing crop damage be retained in a significant format at the end of the process itself? To do that, we set up a test to look at the effect of the process, so the entire process, on the benefits of crop damage. This was a more intensive test, or more extensive test, where we looked at, so again, contamination on carcasses with intact or damaged crops, starting from after the eviscerator, going through to after the outside washer, and then through, again, the automated filleting machine to the end of where we had the fillets at the end of the process. We also looked, in that case, at clean versus used lines as well. I will make it brief. The results you obtained are shown here. These results show you what we call the microbial benefit, let's say, of preventing the crop damage, which is the difference between contamination levels when we have crop damage compared to when we do not have, or when we have intact crops. And you can see that, although the benefits do decrease over time, so in the process, they still remain quite large, even or significant at the end of the process. So at the end of the filleting line, you still have an 0.7 log benefit in terms of the Enterobacteriaceae, and as much as 1.0 log benefit in terms of the lactic acid bacteria. So that means that we could potentially improve not only the food safety, but also the shelf life of breast fillets by simply preventing crop damage or minimizing crop damage at the evisceration point. Now, we thought we had finished our work, but more recently we discovered an additional source of contamination of that tissue, and that is what is called what we call the cloaca puddle, for lack of a better term. And that cloaca puddle simply, I hope you can see it in the picture, is the water that sits under, just below the cloaca, between the legs of the birds, and it's normally visible from the picking, after picking, and through to the evisceration department. There you can see that water. It's about 8 to 12 millimeters on average, and we determined that it was quite contaminated. And then we determined that that cloaca puddle can enter the cavity of the birds when the vent is opened. It enters the cavity of the birds when the vent is opened, and in the pictures you can see it then is able to, so we were able to see this by staining that water with a blue colorant. It then is able to stain, you can see in that area, the cloaca area mostly, and also part of the crop area membranes lower down in the carcass itself. So already an indication that the crop area tissue could be contaminated at that part. Then in the second part, we followed through the evisceration or the eviscerator, and we determined that after the viscera pack has been removed, that cloaca puddle, so now the entire cavity is blue, it's actually spread over the entire surfaces of the entire internal cavity, and all of the viscera packs are also colored blue, which indicates they're also contaminated by that cloaca puddle. And importantly, there we noticed that that crop area tissue was also intensely colored with that, with the cloaca puddle, indicating that there is a great potential for contamination of that area with water, that water that simply sits between the legs after the defeathering process. So a simple action can be done here. You can remove that cloaca puddle to reduce not only risk, but also the level of contamination. Then I'll come back to that reduction of the contamination of the breast pellets. We now propose, this is an integrated approach. You need to start with your feed withdrawal to reduce the microbial load or content within the crop. You can then reduce also or remove the cloaca puddle to reduce the risk and level of contamination coming from that source. But also, we are working on ways, for example, of trying to minimize, let's say, damage of the crop during the process, which will limit as well, let's say, contamination of that area. But also then, you should keep the filleting lines as clean as possible during use. And I have an example there that we have customers who have multiple filleting lines, and they actually use one line and keep one line free, so that after about 45 minutes or an hour of use, they can move to the next line to allow them to clean the line they were using. In that case, they can prevent the lines from becoming highly contaminated and contributing to contamination. To end my presentation, I will go through a few perspectives on this. So the first is that microbial load reduction requires really an integrated approach. All levels of the process, the poultry processing chain have to be taken into consideration, starting from rearing or breeding right through to the end of the process itself. Challenges we foresee in the future regarding microbial load reduction: first of all, the ever-increasing line speeds. We are now at 15,000 birds per hour. It is forecasted that maybe within the next 3, 4, 5 years, we will be at 18,000 birds per hour. There could be problems at that stage with integrating most of the current, let's say, interventions that exist. Another, let's say, challenge is the increasing antimicrobial resistant or multi-drug resistant. That may result or have an impact on the efficacy of certain microbial interventions. Also, there's a challenge that we expect that there's on the horizon, the chance that the regulations can become even stricter. The EFSA has already said that the public health burden due to Salmonella and Campylobacter in Europe is still too high, and that to reduce it, they still are thinking of introducing even stricter regulations in the poultry processing industry to bring this down, as fish poultry is a leading food vehicle for campylobacteriosis and salmonellosis. Now, opportunities themselves to end this, we see opportunities. There are a lot of novel, let's say, techniques or methods that have been discussed. On Monday, there was that session from the student competition on microbiology and food safety, where a lot of these were discussed. But for us, the problem is still application itself and the practical application in the commercial level, and also the costs as well, or integration into existing lines. And then also what I can consider as another opportunity is that, and I really like it, we see a lot more publications whereby these high throughput molecular techniques, such as next generation sequencing, are being used to look at the microbiome throughout the poultry process. This allows us to get more, let's say, insight or greater insight into the contamination mechanisms, and I think this will allow us to develop more, let's say, suitable or better bespoke solutions to address the microbial challenges that we have in the fresh poultry processing industry. I'd like to thank you for your attention.